Welcome to this episode of Eureka, and we are going to have a really interesting conversation with Dr. Ashoke Sen, who is a professor at Harish-Chandra Research Institute in Allahabad, which is a constituent unit of Department of Atomic Energy. Well, we all know that everything is made up of atoms. And of course, in school you would have read that atom itself is made up of smaller particles called proton, electrons, neutrons, and so many other things. And today physicists are saying that even particles like proton and neutron are constituted by even smaller particles called quarks. Is it the end? Is there something behind it? This is the kind of question that we are going to discuss with Professor Ashoke Sen in this conversation. But before we continue with our conversation, let's take a quick look at his brief profile. Keep watching Eureka, we are going to have a very interesting conversation.
Professor Ashoke Sen is a renowned Indian theoretical physicist and distinguished professor at the Harish-Chandra Research Institute, Allahabad. Born in Kolkata in 1956, Professor Sen completed his BSc in 1975 from the Presidency College, Calcutta. He studied thereafter at the IIT Kanpur for his master's degree and then moved to State University of New York, Stony Brook, US for his doctoral work in physics. Professor Ashoke Sen is recognized for his important contributions to string theory that forms a vital part of mathematical physics today. His initial work on duality established a surprising connection between the weak and strong coupling regimes of the string theory. Other contributions include the entropy functions of the black holes and its application to attractors. Professor Sen has won various national and international recognitions. In 2012, he received the world's biggest prize in physics, the Urey-Milner Award, for his contributions to string theory. He also received the Padma Shri in 2001 and the SSB Bhatnagar Award in 1994.
Thank you for being with us in the show. It's really wonderful stuff. So
Thank
let me start with this question. All of us who have gone to school know that everything is made up of atom, and inside this atom there are these three particles: electron, proton, neutron. Is that so?
Yes, that's certainly true. Atom has a central nucleus which has made protons and neutrons, and then there's a cloud of electrons around it.
So is that the end? I mean, that's the kind of understanding that we had.
That's certainly not the end. I mean, we know now that protons and neutrons have even smaller constituents, which are called quarks, and the particle that binds them is what are called gluons.
So you mean to say like for example, in a building you have bricks, and then in between there is mortar which binds. So there are also particles which bind these things together.
Exactly.
Yeah, what are those particles called as?
These are called gluons. They mediate the strong force between the quarks, which actually bind them together.
If one has to understand what is this strong force, because that's something that we have not commonly heard of. We have heard of something like gravity, which is like all of us are familiar with. We are also heard of things like, for example, heat. I mean, in school that's what you read. Then you read about light. Maybe if you read a bit more, I mean, maybe you read about electromagnetism. Light is nothing but electromagnetism, right? But then what is this strong force? I mean, how do you, in a very simple way, explain this?
Well, you can, already guess the existence of strong force once you accept the idea that a nucleus is made of protons and neutrons. Okay? We know, for example, that neutrons are chargeless, but protons have positive charge.
Okay.
And you also know from our lessons in electrostatics that like charges repel. Okay? So then the natural question would be, what binds the protons together?
Okay.
Why aren't the protons flying apart from the nucleus?
Oh, okay.
And strong force is the force that binds them together.
Very interesting. So you have this nucleus which is actually positive charge and a cloud of electron. So you can assume that the cloud of electron is kept there by this positive charge.
That's right.
But then the question comes in that how is the positive charges?
Exactly.
Because there are more than one particle inside the nucleus. How are they sitting together without actually fighting with each other and going away? Right? So this is what you call as strong.
Yeah. So this is one of the manifestations of the strong force. Okay. Of course, it has many other manifestations. For example, the quarks are held together inside protons and neutrons also by the strong force. but at the level nuclear level is the place where you first encounter strong force. Yeah.
So it's only beyond that if you go actually you encounter strong force. Otherwise, in your daily life you never encounter strong force at all.
At large distances, the strong force is very small, so you don't really feel the effect of strong force.
So if you have a nuclear power station, it's actually the strong force which we are converting into energy, right? That's where, in some sense, in modern times, we are actually putting to use the strong force.
Exactly.
Is that right?
That's right.
Yeah. That's very interesting. Okay, so let's continue this story. You have this atoms. Inside the atom, there are particles, electron, proton, neutron, and then you now say that protons and neutrons are made up of quarks, not electrons, right?
No, not electrons. Electrons are still thought of as fundamental particles.
So now this protons and neutron itself is made up of quarks.
Yes.
Is there something smaller than quarks?
Well, as far as we know today, there is nothing smaller than quarks. But what we do know is that quarks and electrons are not the only elementary particles. There are in fact large number of elementary particles which have been discovered, and they are discovered basically by hitting the protons against each other at very high energy, and in that process it produces other elementary particles.
Okay, so it's like, for example, a child, when you give the child a small toy, she, breaks it up or shakes it up, or take off together to see what's inside. That's a kind of thing that, in some sense, the child, a scientist is also doing.
That's right.
Is that,
Yeah.
So how exactly this thing happens? Is there a simple way you can tell me, like how do you actually look at something which cannot be even seen by eye?
Yeah. So basically, you use light at the analog of light. Okay, because you know that for seeing anything we need light. Okay, but to see smaller distances we need light whose wavelength is smaller. Okay, and then there is a theory which is called quantum mechanics, which tells us that the smaller the wavelength, the larger the energy. Okay, so to produce light of very small wavelength that can be used to, for example, probe the structure inside a proton or a neutron, we really need very high energy particles. And that's what we do, that we accelerate two particles at very high energy and let them collide and see what comes out. And then from that observation, we reconstruct what might have been the force inside.
Okay. So this is exactly what was kind of experiment people were doing in what is this place called CERN,
That's
which
right.
kind of became famous few years ago for discovering something called God particle. We'll discuss about that. So in this collider, what you do is that you send two protons from two sides and then make them collide with each other.
So you first of all accelerate them in a circular orbit, and then at some point you make them collide, and then there are detectors which observes what happens when you make them collide.
Okay, you said that it's not just quarks and electron, but there is a zoo of fundamental particle.
That's right.
So is there a number that we know now?
Well, yes, we do know a number. I cannot tell you immediately what the number is. I can probably count one by one, but let's not do it right now. But there is a theory called the standard model, which predicts a certain number of elementary particles, and all of them have been discovered by now. Okay,
You
the
mean to
last
say that
one
all the particles which are predicted by standard model has been discovered?
has been discovered. Yeah, the last one was a Higgs. So the standard model was formulated more than 50 years ago, and Higgs was discovered only a few years ago.
Okay. So let me ask you another question. You said that we predicted through standard model and discovered particle. So one of them is Higgs particle, which is popularly called as God particle. Okay. But is there any other particle which has been discovered in the same fashion?
Yes, for example, the mediators of weak force, the W plus, W minus and Z, these are three particles that were first predicted by the standard model, and then they are found to exist.
Okay, that's a very interesting point. You also in between said something very interesting, which I want to bring back to the discussion, which is you said there are some particle called gluon, which actually binds the quarks and keep them inside the proton or a neutron.
That's right.
And you call them as a special kind of particle.
From the point of view of fundamental physics, all of them are particles. Okay. They play a special role in the sense that they are the ones which mediate strong force. Okay. But every particle in some sense mediates some force. Okay. It's just that those forces don't have specific names. Gluons are specific particles which mediate strong force, just like the W plus, W minus and Z that I mentioned. They mediate weak force.
They mediate weak force.
That's right.
Now let's use this word called weak force.
Yes.
Like we understood strong force. This is also a new term. So how do you simply explain what is this weak force?
Well, weak force is weaker than strong, as the name suggests. Okay. But and for many purposes, you can ignore the effect of weak force. Okay. But for example, for explaining certain types of radioactive decays, okay, you can show theoretically that it's not possible if strong force and electromagnetic force are the only forces in nature. Okay. So you have to postulate a new kind of force, okay, and that's what is called weak force.
Okay, so it's what makes, for example, sometimes the spontaneous disintegration of a neutron into a proton and a electron, right?
That's
so what we sometimes study in +2 as beta decay,
That's
right? So that's where the weak force comes into play. Okay, so we know electromagnetic force, we know gravity, and then there's two new forces, strong force and weak force. Are they the only four?
Well, again, as I said, every particle mediates a force. So if you ask a scientist, they will add more. Okay. For example, the Higgs particle is there. Higgs particle also mediates a force, right? Whether you call it weak force or a new kind of force is a matter of taste. Okay. These are the four major kinds of forces, okay, that are normally referred to. But when you talk about the standard model, okay, it's one single theory which tells you what will happen when you perform a given experiment. Okay. And in that process, all particles play roles.
Play a role. Okay, fine. Very, very interesting. I mean, we'll continue this conversation. We may need to take a very small break. Don't go away. Keep watching Eureka. After the break, we are going to have a discussion about what is the so-called God particle. Keep watching Eureka. Don't go away. Welcome back to this episode of Eureka, and we are having a really interesting conversation with Professor Ashoke Sen from Harish-Chandra Institute of Research in Allahabad, which is a constituent unit of Department of Atomic Energy. It's very interesting. Before the break, we discussed about, let's say, how things are made up of. You know, once upon a time, we thought everything is made up of just atoms, but we know now that there are a lot more to it.
That's right.
We talked about four major forces. Electromagnetism, which we sometimes call as light, or even X-rays are electromagnetic waves, radio waves are electromagnetic waves. All of them put together, we call them today as electromagnetic waves. Gravity, everybody knows. You jump, you fall down, everybody knows. Then you introduce us to two new forces, strong force and weak force.
That's right.
These four forces, if I'm going to ask you, is there any very interesting features associated with what would you put them as?
Well, one of the interesting features is that the gravity and electromagnetism are long range forces. That's the reason why you are familiar with them in everyday life. They act over even when the distances are very, very large, whereas strong and weak forces are short range. Okay. That they operate at the nuclear scale, okay. But once you go beyond nuclear scale, you see that their effects have
almost, I mean, you can't even measure it.
You can't even measure it.
That's a level.
It happens for different reasons for strong force and weak force, but both of them have this particular property that beyond a certain scale you cannot even measure it.
Okay. See, let's look at these two forces which acts on long range, gravity and electromagnetic.
That's right.
How would you compare them?
Well, at long range, that at the scales that we are familiar with, the gravity is very, very weak. It's just almost negligible compared to electromagnetic force. In fact, you can do a simple calculation based on just high school physics. You calculate gravitational force between two particles, say two protons, by using the Newton's law of gravity, and you calculate the electromagnetic force or electrostatic force by using Coulomb's law. Okay. And you will find that the ratio of gravitational force to electromagnetic force is like 10 to the minus 36, which is you write 36 zeros after 1 and divide 1 by that number. Okay. That's how small gravity is.
That's a small part. That's a insignificant. I mean, that will be so small. So that's a kind of range.
That's right.
Yeah. So in some sense, you can say that 10 to the power of 36 times more.
Exactly. Electromagnetic force is 10 to the 36 times more.
Very interesting. Actually, many of you still remember your high school, higher secondary school physics, or you can just access those books. Why don't you go and try it? I mean, it will be a very, very interesting exercise, I'm sure. Yeah. Let's continue with this story, and then before the break, I sort of promised my viewer that we will discuss something about this so-called God particle. First of all, why you scientists name this particle as a God particle? I mean, is it the proof that God exists or what?
I don't think the scientists actually named it as God particle. I mean, the story that I have heard is that Leon Lederman, who was a very famous experimental physicist, he was writing a book, and he wanted to call give the title of the book the goddamn particle.
Goddamn particle.
Goddamn particle, because we couldn't just find it. And
It
the
was
editor,
so difficult to find.
exactly. But the editor didn't like the name, so it was changed to God particle.
Acha, okay. So it's by accident that it got a name God
Exactly,
particle.
and no scientist ever refers to it as a God particle. We call this the Higgs particle.
Yeah. So can you tell us something more about it? Why it was so famous? I mean, everybody talked about it when it was discovered, and everybody said that it's a discovery of the century and things of that kind. Like,
Yeah, I think Higgs particle is so famous because it was something that was predicted by the Standard Model, which is the current theory of particle physics that we know of. But it was not discovered for many, many years. Okay, of course, many other particles are also predicted by the Standard Model, but it didn't take so long to discover them. Like W plus, W minus and Z, they are also predicted by the Standard Model, but they are discovered within 10 years or so. Okay. Maybe a little more than 10 years, but not this long. Higgs particle was the last particle that we knew had to exist if Standard Model is to be right. If Higgs particle was not found, then you have to really rethink about our understanding of nature, and that's why discovering Higgs particle was such a big news.
okay, fine. So one is that it was one of the most difficult thing, and then we were able to find it at last.
That's right.
That's a
Yeah,
kind
and also it illustrated the power of logic. That I mean, even though we didn't see it, right? I mean, logic dictated that it must exist. Otherwise, it will be very hard to understand nature. Okay? And finally, it did happen to be discovered.
Very, very interesting. Now, let's shift to your area of research, which is you are planning to go beyond Standard Model.
That's right.
That's right. So, which essentially mean that the Standard Model should have some kind of a gap.
That's right.
So, what are all the major gaps you think the Standard Model has?
Okay, there are some gaps which I will call not a major gap, it's a more minor gap, okay, which is, as one example, that there are particles called neutrinos in the context of Standard Model, and Standard Model strictly predicts that they should have zero mass, okay, that within Standard Model neutrinos cannot have mass. And this is what we had thought for a long time, till about 20 years ago it was discovered that the neutrinos have very, very small but non-zero mass. Okay. And that showed us that Standard Model cannot be the final story, right? There must be some modification of the Standard Model that is necessary. Okay. But these modifications are not major ones. Okay. There are, without giving up any of the basic principles, one could.
So, if one has to take an analogy, it's like, for example, before Newton, people thought that Earth is a globe, but whereas Newton came and said that no, it's not a perfect globe, but there is a kind of a tap on the North Pole and a tap on the South Pole, something like that.
Yeah,
I mean, yeah.
That's
okay. So that's a minor gap. So what will be the major gap?
The major gap has to do with gravity. That right now the Standard Model is based on what is called quantum theory. That's the framework that one uses for describing small particles. Okay. And the strong, weak and electromagnetic forces have all been incorporated into the Standard Model. Okay. But gravity has not been incorporated into the Standard Model. And the reason that it has not bothered us very much so far, or bothered the experimentalists very much so far, is because of the fact that the gravity is so weak. Okay, at the level of the experiments that we are able to do now, gravity is very, very tiny compared to all the other forces.
So you said that it's 1 by 10 to the power of minus 36. I mean, that's a kind of.
It's a 10 to the minus 36.
Yeah.
So it's a very, very small force. Yeah. Okay. But we know that this cannot be the full story, because one can certainly imagine experiments, okay, which will involve accelerating particles to an energy which is much higher than what we have achieved today, okay, and colliding them together, where gravity will be as strong as the other forces. Okay. And in that context, if you want to know what would be the result of that experiment, okay, we cannot explain it without understanding gravity. Okay. And the Standard Model does not incorporate gravity.
Okay, so what is this idea that you are working on, you and your colleagues are working on? Maybe there are a lot of people around the world who are working on this, which tries to go beyond Standard Model.
Yeah, so the subject that I work on is called string theory, okay, and as the name suggests, it has something to do with strings. Okay. And the difference between the kind of principle that one uses for standard model is that in the context of the standard model, one thinks of the elementary constituents as particles. Okay, they are like a structureless object. Okay. In string theory, the idea is that the elementary objects are not particles, but they are like strings, one-dimensional objects, okay, which are nevertheless very, very tiny. Okay. You can also estimate what the size of such a string will be just using string theory, and you find that this is much smaller than what we have proved so far.
Very, very interesting, very, very interesting. We need to continue this and then explore this a little bit more, but then we need to take a very short break. After the break, we are going to discuss about, are we all made up of strings? What are strings? What do they mean when they say it's a string? All these questions we will explore after the break. Keep watching Eureka. We'll take a very short break. Welcome back to Eureka, and we are having a really interesting conversation with Professor Ashoke Sen from Harish-Chandra Research Institute from Allahabad, which is a constant unit of Department of Atomic Energy, and he is working on a very interesting field called string theory. Before the break, he was kind of making a statement that we are all made up of strings. Are we all made up of strings?
Yes, if string theory is correct, we are all made of strings.
So it's like we are all violins.
That's right, yeah. We are, well, our constituents are all violins. It's like that.
That's nice. I mean, we'll have a very musical life in that case. Yeah, good. So what is this string theory, if one can explain?
Yeah, so in string theory, the basic idea is very simple, in fact. Okay. In elementary particles, as I was describing the elementary particle physics, the basic concept is that the constituents are particles.
It's like a small, tiny ball. I mean, even if we don't actually believe it, that's a kind of imagery that we have. Yeah, okay.
And then there are these different kinds of particles. So we talked about electrons and quarks, for example, and gluons. Okay. In string theory, the idea is that everything is made of tiny strings, okay, and there is only one kind of string. There are not different kinds of strings.
It's even really mind-boggling, meaning that all the hundreds of fundamental particles that you see are actually nothing but one string producing different music.
That's right, exactly. So it's like one kind of string vibrating in different modes, okay, which may differ in frequency, differ in amplitudes, and these different elementary particles are just different manifestations of that vibrating string.
Very interesting. So it means like this musical instrument has just only one string.
That's right, exactly.
And by playing
One
it.
kind of string. Of course, different elementary particles are different strings. One string vibrating in one mode, the other string vibrating in another mode.
Another mode.
There is only one kind of string.
Okay, okay. Yeah. That's interesting. If I ask you, I think people have been trying to develop this string theory for at least more than 2-3 decades now. Where are you in this quest?
So first, the major success of string theory, and in fact that is the reason why string theory became popular in the first place, okay, was the discovery that string theory actually contains gravity. Okay, I talked about earlier the elementary particles. I mentioned, for example, the gluons, which mediate strong force, or W plus W minus and Z particles, which mediate weak force. Okay, there is also a particle called photon, which mediates electromagnetic force. Okay. But there is no particle called graviton in the standard model, okay, which would have mediated gravitational force. So one of the discoveries in string theory, and it in fact took 10 years to discover this, is that the vibrating strings actually contains a graviton. Okay. So gravity is something that you don't put in string theory. It's an outcome of string theory.
It's already there.
It's already there. In fact, it's impossible to have a string theory without gravity. Okay. So that was the first major success. Okay. But then, of course, people knew that if string theory has to explain nature, it also has to incorporate all the other three kinds of forces: strong, weak electromagnetic force. You have to find the quarks and electrons from vibrating strings and so on. Okay. And that's where much of the effort has gone in string theory. Okay. We have certainly come very close to, well, I don't know how close, because unless we reach the end, we don't know how close.
It's like an uncharted terrain. You can't say that how long you are going.
How long you are going. Okay. But certainly we have understood the mechanisms by which the strong, weak and electromagnetic forces could come in string theory. Okay. What we have found is that string theory has many different phases, states that it can exist in, and there are many states in which we have particles like quarks and particles like electrons, forces like strong force and weak force and so on. Okay. But to really establish that string theory describes nature, we have to find one particular state of the subject, or one particular phase. I mean, these phases are like phases of H2O molecules, right? We know, for example, H2O molecules, even though there is a single kind of molecule, it can exist as water, ice or steam.
Yeah.
Okay. Similarly, string theory, even though The theory itself is unique, it can exist in these different phases. Okay. And the idea is that you have to find the right phase which describes exactly what we are. Okay. And that we don't know how long it will take to find it, right? Or whether we will ever find it, because that's what will establish if string theory is right.
That's where the exploration is actually going
exactly.
on. Yeah. Very, very interesting. And if one can recall, there are some people who say that in some sense the whole string theory is kind of dead. It's come to a dead end. What's your take on it?
Well, I think the people's argument that string theory is dead is because string theory has not made connection with nature yet. Okay. But of course, in science we can never say how long it takes for a subject to make contact with reality. Okay. I would say the string theory will be dead on different ways. It can be dead in different ways. One is that if we could ever do an experiment at a scale at which string theory predicts differences from what normal quantum theory of particles will predict. Okay. But that energy scale is very, very high, and it will not be achievable in the near future. Okay. The second way it can be dead is if somebody finds a theory of gravity which is not string theory, okay, and which is fully self-consistent. I mean, in fact, one of the reasons why string theory has not been dead is because it is a fully mathematically consistent theory. People have tried to find various flaws. I mean, there are many ways you can test string theory, not experimentally, but by mathematically. String theory predicts various mathematical identities, any of which could have been wrong, and that would have proved that the theory itself is not consistent. Okay. And every time it has been found that even though mathematicians didn't know of those identities, okay, none of the identities have been turned out to be false. Many of them have been proven. Some of them are still to be proven, okay, but none of them have been found to be false.
That's a very interesting point. This brings me to a different issue which I want to raise with you, which is like you have been doing science for many years. I mean, quite obviously you got many awards, which goes to show your intelligence, but you don't seem to be making too much of money.
I mean, scientists really don't work for money. I mean, I would say that if you are a scientist in India, okay, you make enough to live a comfortable life. Okay. You will not be rich, okay. But that's not what science is about. I mean, scientists want to do science because they want to understand nature, okay, and I think that's the main motivation for all scientists.
Okay, but what is the satisfaction that you get out of this?
Well, when you discover something, okay, that is like it's something that you know which nobody else knows, and you have
at that point of moment, you are
exactly.
the only one who knows it.
That's right, and you have to tell the world that this is how things happen.
That's very, very interesting, and we had a very interesting conversation, and also very interesting, exciting insights into what the world is made up of, beyond what we have studied in our school textbook, and you had explained it very, very nicely and very interestingly. Thank you for being with us. Thank you for watching this program. Keep watching Eureka. We'll come with another conversation, same time next week with another Indian scientist. Keep watching Eureka.